So welcome to a fun and exciting panel on solved problems and visualization. So around 10 years ago, roughly, let's say, there was kind of a wave of discussion and literature on the top unsolved problems in visualization. Right, everybody knows Chris Johnson's paper on that topic. There's an IEEE VIS paper on that topic. And a few other, there's the NHS discussions on the top challenges and unsolved problems in visualization. And then there are a few less known publications on the topics. By the way, there's one on top unsolved problems in multi-field visualization that's not too old, if anybody wants to check that out. Anyway, there was a lot of discussion around 10 years ago, roughly, plus or minus 3 years. So the implication of that is that there are solved problems in visualization. Whoops. So if there are lots of unsolved problems, then the implications that there are solved problems in visualizations as well. So that's what we're here to talk about. What are the solved problems in visualization, right? You may have wondered what you should be working on, right? What you should do with your life. What problems have we actually solved as a community over the last 25 or so years? How do we define what a problem is? What we call an open problem or a solved problem? When is a problem considered to be solved? Right? And have any of those challenges that we identified 10 or 20 years ago, and then I learned at the keynote that this was also a theme in 1993 about the top unsolved challenges. So have any of those been solved? And then of course, what about visual analytics? So actually Bill's going to tell us all the solved problems in visual analytics. Anyway, so it's going to be really exciting to hear about the answers to all these questions. So each panelist will speak for about 10 to 15 minutes. Then we'll open up the discussion to the audience for questions for about 30 minutes. We have a really great set of panelists here. We're going to go in alphabetical order, starting with Chris Johnson. So it'll be Chris, Rob, Penny, Bill, and then Tom at the end. Tom wanted to be last for some reason. He wants to have a big surprise, I think. Some very special slides, I think he has. And then we'll have optional concluding remarks. Sound good? Let's start. So welcome to the stage, Chris Johnson.
Good afternoon. Thanks, Bob, for inviting me to this interesting panel in which we will explore, are there any solved problems in visualization? If so, what are they? How do you know if you've solved a problem? So in the last while, 10, 20, however many years people here have been working on visualization, some longer, we've spent a lot of time coming up with new techniques, new abstractions, new mappings from data to our visual system. So we have streamline advection, we have volume rendering, we have topological problems, we have problems in microscopy, we have streamlines, stream tubes, we have geometries, and of course we have a lot of problems in informational spaces, information visualization and visual analytics. So the question is that have we solved any of these problems along the way? So I'm going to frame this in an area that I've done some work in myself and that I think has a really rich history within the visualization community, and it's with isosurface extraction. I think that as visualization students, especially in scientific visualization, that isocontouring and isosurface extraction, marching cubes, is the first algorithm that people often code up or get to learn about, especially for three-dimensional visualization. It's often one of the simplest algorithms to go about. So when we think about isosurface extraction, we generate, we're going to render these images, search, construct, render the images, and then as this went along, we started to do pre-processing, and then there were a set of algorithms. There's the original paper by Rheingans and marching cubes. There were octrees, extremographs, sweeping simplices, which was an unstructured grid, unstructured mesh one that Han Wei and I did. And then Yard and Livnet came up with something called the span space, in which he could actually put a bound on the complexity for the near optimal isosurface extraction, which was order square root of n plus k. And then there was another group that then went on to prove the optimality of the isosurface algorithm. And so for the search of this particular algorithm, then it was optimal. So the search phase was proved optimal. All right, and then the question became, how do you do better than optimal? And basically it's how you ask the question. Because if a polygon falls on the view plane but no one can see it, does it still exist? Is it still important? And the answer basically is no. And this is the idea. Now your bottleneck is, now that you've got the search phase optimized, now your bottleneck is the construction part and the rendering part, which are order k, which is the number of triangles that you've created on your surface. Well, if you don't see the ones that are in the back of the surface, then you can use a view-dependent approach. And then now you've reduced the overall complexity instead of the search plus order k, now to order view of k plus order view of k and the search algorithm. And this made tremendous differences in terms of the size, order of magnitude speedups in terms of the isosurface extraction. The rendering times here are old, I will say, but just look at the number of polygons, reductions, and then just the order of magnitude speedups. And then you ask the question, okay, so how do you do better than this optimal? Well, why are you using polygons in the first place? Is that the best way to create isosurfaces? Well, it turns out no, in terms of speed, especially for very, very large systems. And so the question is, if you're actually making polygons, going and constructing these things and trying to render things that are less than your triangles are less than a pixel, you're probably wasting your time. And so there was a set of papers, Yard and Livnet and Trikosh wrote, and others started doing these point-based systems in which you could speed up the isosurface interaction process by a huge amount. And then there are also the parallel ray tracing methods. We're not going to create any kind of primitives for triangles at all. Why bother to create those triangles? And so basically what it came down to, if you looked at this, is in the beginning, that bottom chart, the bottom line there, that's marching cubes isosurface extraction. And so that solved a problem. That was the first paper that solved a problem of creating surfaces from volume metric scalar data. And so it did solve a problem. Did it solve it the fastest, the most scalable? You can start putting all of these qualifiers on what it means to be solved. And so then we had different methods that changed the constant, basically. So that sped up things almost an order of magnitude, but not entirely. But then we got order of magnitude changes, and that was the search phase. So that is optimal in terms of the search phase. But then we stopped making triangles all the time or at all, and then we started getting these, many order of magnitude speedups. And then you ask the question, is this solved? Okay. So I went back and I started looking at all the papers kind of in a history. And in 1985 to 90 is when the first isosurface, that's first marching cube paper came out. And then there were multiple papers that followed onto that quickly. There was a redundant case that came out. There were other forms of marching cubes. People were doing the octree in different data structures. And this continued. And you'll see that the number, and the way I got these, by the way, is that I just did simple Google Scholar searches where it was required to have either isosurface extraction or marching cubes in the title. If you just put it anywhere, there's thousands and thousands of papers. But I thought this would at least tell us that marching cubes or isosurface extraction was the main theme of the paper. And you keep looking at this over time, and you see it's getting popular and more popular. And then around this time, 2010, it's gotten less popular over the last years, and this year we have 10 papers. So one thing you can conclude about this is that there's been a lot of work done in isosurface extraction. There's a lot of papers written about it, and that maybe it's becoming a mature field. There has been a lot, and there might be only incremental gains to be had about this. But if you look at some of these 2015 papers, what you'll find out is that some of these are about very specific applications to isosurface extraction, so optical fiber and endoscopes, based on 3D model transactions of in indoor environments, and then one by my colleagues at Utah, Mike Kirby, on now doing uncertainty approximations with isosurfaces. So extending the isosurface algorithms, if you will, to include uncertainty. But if you look at this, you don't see anything that's like a new algorithmic improvement on this until I came to this conference and went to the LDAV symposium where Will Schroeder introduced Flying Edges, a high-performance scalable isocontouring algorithm, which was another way to get more speed up out of fundamental isosurface extraction. And I think people were very impressed because most people, including myself, thought this is a pretty much solved problem in visualization. But he showed that under certain circumstances that he was able to actually improve the performance of the isosurface extraction again. So I guess where we're getting to is it really depends upon the meaning of the word solved is. And if you look at this, and you go to any dictionary, it basically will come up and say what solved is to find an answer to, explanation for, or means of effectively dealing with a problem or a mystery. And so depending on your view of what that is, then I think you can decide whether problems are solved or not. So the way I thought about it was, I think that we can prove algorithmic complexity in mathematical ways for certain constraints, and those can be thought of as solved problems in that limited sense. So you can prove that, you know, the search phase of isosurface extraction, if you're using triangles and if you're doing these things with all the particular qualifiers, you can prove that that's at least a minimal complexity. A lot of the other types of maybe solved problems, or I really think of as optimization problems. So I think we see a lot of papers that are showing they can optimize a particular hardware or a particular system. So it can be, there's a lot of papers on GPUs and isosurface extraction. So for certain types of GPUs and for certain types of primitives, triangles or ray tracing or whatever it is, that they can show that they can have an optimization or an optimal algorithm. And it's also the case that a lot of the papers that are out there are trying to optimize some of the work that we have done in the visualization community, but really tailor it for a very specific application domain. And I think those might be, in the sense of optimization or an application, you might consider those may be solved. The other, when I was talking to some people about what a solved problem was, the one answer I got, which I thought was pretty good, was by Timo Bremer. It's all the visualization problems we aren't working on because they are solved. So with that, I will thank you, and I'm looking forward to listening to my other panelists and hearing your thoughts on the matter. Thanks.
So solve problems in visualization. Chris picked on the word solved. I chose to pick on the word visualization. So what is visualization? It's the process of representing abstract business or scientific data as images that can aid in understanding the meaning of the data. That's from whatis.com. Keywords there are highlighted, obviously, representing images and meaning, all right? Webster's Dictionary, the act or process of interpreting in visual terms or putting into visual form. And then Robert Cacero's got several pieces, and so I pulled one of them, 3 highlights here. Based on non-visual data, I will expound upon that in just a second. It's got to produce an image. I will anchor on that one. And the results must be readable and recognizable. That actually may be more applicable to some of the slides I've seen this week, but we'll keep going with that. So what is non-visual data, or what kind of data do we start with in doing visualizations? Are there things that are too small for us to see with the naked eye? Protons, quarks, atoms, cells, molecules, etc. Are there things that are, we're trying to look at or visualize things that are too big? Donna Cox picked on, I think, solar flares. We've done a lot of work in ocean currents, continental land cover. When you think about the big things, though, in a lot of cases, if you get far enough up, you can see them. But there's some things that the naked eye simply cannot see. We may be able to see the effect of it, but wind, heat, salinity, electromagnetical forces, and inside the human body. And granted, inside the human body, we can also often probe, but many times we don't want to poke something in there. So 1987 seems to be kind of a landmark year that we all appeal to as a benchmark. So what has happened? What's changed? What's enabled problems to be solved? Well, a lot of it's been enabled by technology advances. We have much higher spatial density printers. In the keynote, Donna Cox was kind of implying that. We're at the point now where spatial continuity is almost good enough to give you the impression of reality. It's not a dot matrix printer as we had back in 1987. In fact, I was shocked this summer to find out that some of my students actually had a 3D printer in their dorm room. They said, "Hey, Dr. Moorhead, I could design that in CAD, go back and print it, and I can bring you a prototype Friday." I was like, wow, you know, back when I was your age, that was something only San Diego supercomputers seemed to have. We have high temporal density displays. We're able to reproject these large-scale images at a rate that they appear to be a continuous reality, even monoscopically, even binocularly. We can see, we get the impression of continuous motion. We have high spectral representation. In some cases, I think it's limited only because it's just a bandwidth issue. 12-bit seems to be enough in most channels with the processing that we can put before and after those visual channels. So a lot of the problems we solved have really been enabled by technology. So my thesis here is that we have solved a lot of visualization problems, that we can produce images that are physically realistic to the extent of our ability to perceive. In other words, we can't tell the difference in a photograph and a visualization. Pat Hanrahan kind of referred to this, I think, almost 10 or 15 years ago in a keynote presentation here at VIS. So one little thing I want to dive into is cameras. Robert Cacero's points about, you know, image processing, visualization is an image processing. Well, cameras have come a long way from what they classically were. Once upon a time, it was pretty much a box, a lens, a shutter, and some coated material that was sensitive to light, and you got an image. Now cameras exploit a lot of computation, and there's built-in algorithms. We may not be adjusting those parameters, they're automatically adjusted. A Canon, I use this camera because we're using it in some of the small unmanned air systems that we're flying. For $400, that doesn't include the lens, which is probably almost as much. You can get a camera that's got a 9-point autofocus system. It does scaling and filtering instantaneously almost. It adjusts settings to scene composition. Many of your cell phones probably do this. You can set it on a sports, you tell us the sports image you're taking, or it's candlelight, or it's kids, or it's food, or something like that. There's algorithms in there to do this kind of adjustment. This one camera comes with an image processor. I tried to look up the MIPS or MOPS or whatever megaflops that were in the processor. Couldn't even get it. I mean, it's just, there's so much computational power in there to do so many different things now. Now, what does that processor do? Well, it takes values, i.e. invisible data in one way, that are accumulated in a CMOS sensor due to impinging electromagnetic radiation and processes them. If you go back to that original definition, it takes data, it processes them, and it creates an image, all right? So in one way, I think we can argue that today's cameras are really visualization machines. So one of the biggest things I think that's happened in the last, I'll say 25 years, is our ability to show levels of detail. To start out with the big picture and to zoom down. Back in the mid-1990s, Silicon Graphics demonstrated a tool, a piece of software that allowed one to zoom into various parts of the earth. When they first showed it, it required their largest computer and it used special purpose hardware. In a lot of cases, the problem was the data. You could only zoom into particular places, like the Bay Area. It didn't take long for that to be overcome. So today we have visualization tools that allow anyone on your cell phone to smoothly go from a view of the globe, which is about 10,000 miles wide, more like 8,000, but let's just use a square number here, 10,000, to a view of the size of stores on a city block, which is about 50 feet or 0.01 miles. That's 6 orders of magnitude. Once again, the technology and the algorithms are allowing us to do that, the hardware. Geographical systems can handle 10 orders of magnitude. That was a number that was bandied about back in the mid-90s. So to do a little bit or show a little bit about what we've done most recently, and this is admittedly a little more image processing and visualization, is this is a Google map, and we took a UAS, an unmanned air system out there, flew very low, were able to take data in that orange area there. I'm going to go through this fairly fast. Collect a bunch of images, mosaic them together into one composite. That's an area, an estuarine area they're trying to preserve and trying to understand how the vegetation is changing. As we zoom in on that data, that is an 8-inch wide boardwalk, 8-inch wide board. If I go one more image forward, you can actually see the pixels, the squares, and actually can determine it is half-inch resolution. We'd have to get to 0.06 resolution to actually have 10 orders of magnitude from the globe down to this. But even at this level, they can do things they didn't imagine they could do before. One of the scientists there was able to take that data, compare it to some satellite data, develop a classification algorithm, and show that with the UAS data at that resolution, they could determine where the different habitat, the grasses were. The Spartina and Juncus. One wants its feet in at high tide, the other at mid tide. So as that interface changes, it shows sea level rise. In the past, they've had to go out there with lasers and do sedimentation, elevation tables, determine what kind of grass, do wet chemistry, etc. Now, with a simple 20-minute flight, we can show them every month, every week if they wanted to, every year, how the environment is changing. Another application is in agriculture, production agriculture. That's a quarter stuck in the ground soon after a plant came up. You're pretty well probably challenged a little bit to even see that little green sprout right there in the middle. But we can fly over that with an unmanned air system now. Those plants are a little bit taller, more at a V1, V2 stage, vegetative 1, vegetative 2 stage. When that grows up farther, what the farmer, the producer, becomes interested in is how well is this crop doing. So you can see the image there. With our naked eyes, we can see where there's rows, where there's gaps, etc. They want an automated technique. So now with visualization, I'll call that classification algorithm or detection algorithms visualization here, they can see where density is lacking, where they have high density or they have low density. And they can look at change detection over time. So now they can determine, do I have a pest infestation? Do I have a problem here? Can it automatically come back and tell me, I need to look here? This might be a problem area. There's a neighbor's kid maybe running through my farmland with a four-wheeler. Am I not getting enough water in certain areas? Too much in areas? Am I not getting enough fertilizer? So I'm going to argue, and I talked to George a while back. He wrote one of those 1993 George Grinstein papers, and neither one of us could find it. But in talking to him, what are some of the problems on which we've made some progress? Well, I think we've identified some of the hardest problems. I think we've got a pretty good picture on how to do visualization, the process of doing visualization. We've learned how to address the human-machine interaction a bit, and we've kind of determined where cognitive issues come into play. I wouldn't call this completely solved, but we certainly started to address them. I think one of the biggest things, and Donna kind of indicated this, is the time to solution and the cost to solution. We could put up a lot of images, but a lot of those could be generated 25 years ago. They just couldn't be done as fast or as cheaply. Today we can do a lot more because, as Chris insinuated, taking isosurface as an example, we can do things so much faster. We can get to solutions. Time to solution is so much less. But sure, there's still some unsolved problems. There have been several papers this week talking about personalized visualizations and personalized analytics. Different cultures prefer different types of color maps. There's still optimal mappings for optimal communications, if that remains kind of the holy grail, and I think it does. With that, I'll stop.
Okay, so Bob led off telling you what he had asked us to talk about, proposed that we talk about, and a pattern is developing that this group of people feels pretty comfortable redefining what we're going to talk about and giving you our own spin. And I will stay with that trend to some extent. And I want to talk about a little bit what is solved, what is the meaning of solved, getting back to what Chris said. And once we've declared something solved, what do we do with it, or do we just forbid it from appearing again at the conference? And from this, I wanted to draw on sort of a classic researcher. So Richard Feynman was a physics researcher of great note and also great interest in teaching. And so while he was on the Caltech faculty, one of his colleagues asked him a question and said basically, Dick, explain to me so that I can understand it. Why spin 1/2 particles obey Fermi-Dirac statistics? And so Feynman thought for a second and said, well, I'll prepare a freshman lecture on it and I'll get back to you. He went away for a couple of days, worked on that, and came back to his colleague and says, I couldn't do it. I couldn't reduce it to the freshman level. That means we don't really understand it. So the lens I want to talk about a little bit is part of how we can identify what are solved problems is what can we reduce to a freshman lecture? What can we communicate to freshmen? What can we particularly teach to undergraduates? What can we ask them to do? And so I set out to hopefully look at this through 3 sort of sub-lenses. The first is, what do we specify in our undergraduate curricula? What is collected in the textbooks we use? What do we ask our undergraduates to do as assignments? And so my methodology here is I did the rather ad hoc survey of about 17 visualization course syllabi without the permission of the people who teach these courses. They came from a course collection that we had produced at Dagstuhl in 2014 at the Scientific Visualization Seminar there. They also came from things that I could find by poking around on the web. The first thing I learned is there are basically almost no freshman courses, so this may mean that we understand nothing. There were few purely undergraduate courses. There were a lot of sort of cross courses, and then there were a lot of mainly graduate courses. And so I went through the syllabi and looked at what was mentioned and what did the themes, what did the topics tend to be. I rather arbitrarily identified 16 topics that seemed to appear on some number of them. The things that were in, let me step out. There was a fair amount of diversity in what we call visualization courses. Sometimes we capture that in the title and we call it visual analytics or we call it information visualization. Sometimes it's just under the hood. And so this included things that were called all of those. The things that typically appear, one could argue that this is what's solved, but I think that that first list just tells us what do we think is important, not what are we solved, what do we have something to say about. So things like talking about the characteristics of data or tasks, design, color, perception, basic encodings, interaction, which was the most popular topic across all the courses I looked at. And then some technique things, volume rendering, vectors, flow, graph, and hierarchy. And that's a set of things that if one wanted to be controversial, one could probably call solved in some circumstances. There were things in many of these courses, so 7 to 9 out of the 17, contours and surfaces and high dimensional data. The ones that were in some, graphics, animation, evaluation, abstraction, statistical graphics, topology and geometry methods, spatial and image processing, visual analytics, and then more special kinds of situations in data, so maps, time series, medical imaging, multivariate data, and things that appeared in only a few courses, text and document visualization, medical imaging, geometry and topology, which obviously I moved and forgot to eliminate, data mining, statistical methods, and yet more math for those who love yet more math. The ACM has also taken a stab at this, and they have sort of a, I don't know if recommended is too strong a word, but they have a curriculum. The most recent one happened in 2013 and identifies undergraduate recommendations and categorizes things as Core 1, which is every undergraduate with a degree in computing should know this stuff. Core 2, which is every undergraduate with a degree in computing should know most of this stuff. An elective, which is, yeah, this is cool stuff, but it doesn't really matter if you know it or not. We are in the elective category, just in case you were wondering. Most of visualization comes as a sub-area of graphics and visualization. We are the visualization knowledge unit, to use the terminology, where basically the core of what we do is present structures and relationships and data sets from a wide variety of application areas, and that's pretty accurate. We also, what we do appears in a couple of other knowledge units in computational science, which is more focused on the applications first, and that's the driving there. And also the HCI cluster, where we're scattered across a number of the knowledge units. And so the kind of specific things that are in there, you know, which is a way that you can think of, are these the problems that are solved? Because these are the problems that the ACM says that we are ready to be teaching to undergraduates. Visualization of 2D, 3D scalar fields, including color mapping, isosurface generation, direct volume rendering, including raycasting, transfer functions, segmentation, visualization specifically of vector fields, flow, time-varying data, high-dimensional data, non-spatial data, and then a collection of sort of factors and foundations, perceptual and cognitive, design, evaluation, and then finally applications. That's what happens in graphics. The things that happen in the other two knowledge units, in computational science, it's principles of data visualization, some algorithms, some image processing, and particularly scalability, because that's where it bites you. In HCI, it's more things on the design, user-centered interaction, and evaluation side. Okay, so going back and looking at those 17 classes I looked at, I said, okay, the curriculum doesn't really answer the question exactly of what's solved. Maybe the textbooks will. The things that are there, written, printed in the textbooks, those must be the problems that are solved. And so those 17 classes, they used 9 textbooks, where the most common, the one that had the most courses at the top, going down to the fewest at the bottom. And there were some not insignificant number of courses that just sort of threw up their hands and said, we're just going to make you read a bunch of papers. And so these are the things. Looking at those 26 topics that I identified and how they spread across these texts, you can see that a few of the texts have a pretty wide coverage of, you know, what broadly looks like visualization, and some have really much more limited and focused treatment of them. In some cases, this is probably just indicative of a flaw in my methodology, that I was judging what was in the texts by looking at their table of contents. And some books were rather cute and opaque about their table of contents and didn't have the right keywords, and so they end up not having so many things in my scheme. And then at the end you get to data mining, which is relevant but really not about visualization. Looking at the other side of that, given those topics that are potentially interesting, how many of the texts do they appear in, right? So sort of what is the commonality of those topics? So of these 9 textbooks, no topics really appeared in almost all of them. So the most that something appeared in was in about 2/3 of those textbooks. And these were once again sort of mostly the foundational things: design, color, data task, and perception, and then a few technique and situation kinds of things: statistical graphics, maps, and graph and hierarchy visualization. The technique things are all more from the non-spatial InfoVis side. There were some things that appeared in a few, which means less than 3. This is most of the stuff: graphics, contours, volumes, evaluation, vector and flow, high-dimensional data, text and documents, abstraction, time series, and signal and image processing. And then there's a cluster of things that people who teach visualization courses had defined as important enough that they're spending valuable class time and student effort on it, and it appears in none of these books that anybody is teaching out of. Animation, medical imaging, geometry and topology, visual analytics, and math transforms. That's probably telling as well. Okay, so let me circle back to what does it mean to be solved? And it's probably not a binary switch, right? You're not either solved or unsolved. You're somewhere on a spectrum. There are degrees of being solved, and I think we can kind of recognize these. At some point, and probably what you were hoping to get a list of when you showed up today, is the top of this hierarchy, and that's: here's a piece of software that does everything you need to do, and you just have to think about it. Just use it, you're done. Okay? There aren't an awful lot of things probably in that category, and those things that are in that category we've become bored with. The next is: here's the best algorithm method to do that, but you have to go program it yourself, or you have to download it and make it work and all of that. But we know how to do it, you just have to implement that and make that happen. That's a larger set. Next is, well, this is something we know how to do, but we also know an awful lot about the limitations in the cases where it fails and the things that it doesn't quite do. One level down is, this is a thing that we know we'd like to do, and we can tell you a little bit about its characteristics and what we'd like to achieve. We really don't do it very well yet. And you've seen examples of that. You've probably programmed examples of that. And then, in some ways, maybe even the most interesting is the things that we look at and say, wow, I never thought we'd need to do that. We really have no clue, and we really need to figure out how. And the problems that are before us fit somewhere on that hierarchy rather than neatly split into solved and unsolved. So that brings me back to where I started, and this is what I'm hoping to hear sort of from you and from my other panelists is, if we do get to the point where we classify things as solved, now what do we do with them? What do we do with the things that are solved? Thanks.
All right,
Are you ready, Bill?
I am ready.
Awesome.
For those of you in the left side of the room, I'm the man behind the curtain. And you can ignore me. So I'm going to present sort of both higher level and more idiosyncratic, perhaps, view of solved problems. This could be risky. My solved problem could be another researcher's active area of research. In fact, maybe I'd be working on the problem again sometime in the future, and I'd look pretty stupid if I said it was solved. The other thing is I'm reminded of the old story about the patent officer at the end of the 19th century in the US that said, let's close the patent office because all the ideas have been presented for patents. You could look like a unimaginative idiot. And the reason for this is clear enough if we think about it. It's because these are intellectual problems at the core, and some discovery might be made. Some completely new thing that we haven't even thought of could make the problem unsolved again. So what does it mean to be solved anyway? Are there examples from other fields? When I was thinking about this, I thought back to the time when I was a physics student and Feynman was young. And We used to watch his lectures. There were videos of his lectures. If you looked at classical mechanics in those days, it was a thin little book, even in those days, that was basically an exercise in applied mathematics. It was a set of rules, and you know, you got into the Hamiltonian and the principle of least action and all that, and there it was in this little 120-page book. So that is, it appears, a solved problem. Yet, when you take a look at where we are now with computational mechanics, the problem doesn't look so solved anymore when we talk about very complex systems and how those can be represented and understood. So even in that case, perhaps it's not that solved. Well, we could say, well, are there really any solved problems? We've been talking along this line. It's sort of a Weasley way to get out of it. Let's go home, there are no solved problems. But I'm going to take a stab at it. So I set up this criterion. Well-studied and widely used is my criterion for quote-unquote solved. So with that in mind, I came up with a list, my own idiosyncratic list. And you'll see, I think, that several of these things sort of overlap with other things other people have said. Several of them appear, for example, in textbooks and monographs. So the global terrain visualization problem, 2.5D draped terrain with imagery. We wrote one of the seminal papers back 20 years ago on that, along with several other people. You know, the fact that how you can organize things into GIS databases and use them efficiently, how you can do multi-resolution terrain, importantly, how you can put new data anywhere you want into this system so you can grow this system. That is not to say that 3D stuff on the terrain or segmenting of the terrain imagery, things Robert talked about, or you know, like 3D phenomena over the terrain are anywhere near solved. But you know, we have everything now that Robert talked about. We have Google Earth, which is sort of based on some of the research we and others did. And it seems like a pretty solved problem, at least in that regard. Link multiple visualization layouts. So if you take a look at what the information visualization community has been doing in this area over a period of years, you know, with linking and brushing and various types of ways of representing data scatter plots, you know, 2D data, basically, hotspots and so on. You have this feeling that, yeah, this is the way to approach these data, at least in this instance. This is a solved problem, or at least this aspect of the problem is solved. Now, sort of linked to that last one, standard information visualization interfaces. You know, we now have web service-based tools that most of us that do these type of interfaces, even for research, use. They're very useful tools. They're very effective. They're very expandable. And so, you know, to that extent, maybe this is sort of a solved problem. The study of level services, of course, Chris went over this in a much richer and deeper way than I would. I just point out that this study has been around for, what, 40 years? About 30 years ago, marching cubes came along, marching tetrahedra, asymptotic decider. So at least for certain types of data, and if you're not talking about scale, you're not talking about real complex data, you know, you have the approaches there, it appears. And again, this is something that everybody studies in a basic graphics course. Basic text analytics, this is something that has come along more recently, but if you talk about sort of bag of words techniques, not linguistic techniques, not techniques with lots of semantics added, there seem to be, sentiment analysis and entity extraction. And for that last one, I know there's a lot of work still to be done, but there seemed to be a well-established set of techniques that could be used at least in that regard. I'll say more about this later, about how this perhaps becomes unsolved again. And then, well, here's one that probably could have a lot of argument about. But maybe in terms of basic graph layout techniques and in terms of basic interaction and in terms of ways that you might visualize nodes and links. And you're not, again, talking about extreme scale or high complexity. Maybe this is a solved problem. Here's one that was interesting to me when I thought about it. Cross-platform web design for visualization. We've moved on to other issues, it seems, by and large, and I'm saying that there isn't any work done on this, but doesn't seem to be a lot. I think because we have now these web services platforms that immediately give us, almost for free, capability on a variety of platforms, and to some extent, because we're sort of roped in by the modes of interaction that that the companies that produce these platforms give us, that this is perhaps not, this is a or widely used set of techniques, if not a well-studied set of techniques. So here's some other thoughts. For well-studied problems, differences tend to be application-specific rather than fundamental. I think that we've seen that in some of the problems discussed here. And that doesn't mean that the differences, it's probably the wrong choice of word to say fundamental, because they could be, you know, like real-world problems that are real important and real complicated and require new research. But often the differences tend to be that I think that some of the stuff Chris showed supported that. And, well, there's solved problems that become unsolved. You know, I'm thinking of the problems having to do with the visual interface and interaction, for example. So a lot of work, and you might say that some of this I did, in that area, which is perceptual work, well, you know, there's sort of solved problem. But when you start extending along the continuum to cognitive, to reasoning, to actionable knowledge, to exploration and discovery, then suddenly the problem isn't solved anymore. Let's see, I had another example here. Well, when you add dimensions to a problem, I think suddenly it becomes unsolved. I mean, the best paper in visual analytics conference this year had to do with dynamic graphs. You know, anything you add time to, or if you add uncertainty to, and in the second case, you're really like doubling the number of dimensions, and they're all important, it becomes an unsolved problem again. And so, that's the end.
I had asked our panel organizers to prepare some slides for me 2 days ago. He did not deliver by noon today, so no slides, you have to listen to me. So in contrast to some of my panelists, co-panelists, I've never collected lists of unsolved problems, and I never promised to solve any of them. So thus also the questions raised by our organizers are quite interesting. I will not answer any of them. So since I spent more and more time in management, I learned that it is common and a valid approach not to answer what you were asked. So what I also learned in management is that if you don't want or you cannot talk about content, then talk about structure. This is what I will do now. So visualization is certainly a success story. The keynote by Donna Cox yesterday showed how far we have come in our field, but let me remind you, success does not always come by itself, and people in various roles in our community solved many structural problems over the years, paving the way for our current standing. So my interpretation of solved problems in visualization for this panel is to remind us of what I think what we did right over the years. So first problem, visualization, what is it? I think we all managed together to make visualization widely accepted as a scientific discipline. This is not always, has not always been so, and it's not always obvious. And I remember discussions about the problem of our status, ranging from toolsmiths for plotting packages, or visual statisticians, or visual arts, In my experience, this problem has disappeared. If I get introduced among colleagues as a visualization person, I don't have to explain anymore what this is. People seem to know, and this is really different now. And at the same time, I think we were successful in making visualization an ubiquitous technique. If you just count how many people out there claim that they are doing visualization, they are orders of magnitude more than even 10 or 20 years ago. The second problem I want to address is what belongs to visualization. We as a community are open for new trends and application domains, and we are willing to integrate them. I think this is a really great success. In my early days of the conference, I perceived SciVis and InfoVis as very different animals. And when visual analytics came along, it was not so clear whether all of this would eventually continue to fit together in 1 week. I also remember discussions at EuroVis where people thought about splitting up into 2 different conferences, the SciVis conference and the InfoVis conference. I think that part of our current strength is, as a community now, results from keeping it all under one roof. As a personal note, 10 years ago, I would not have believed that my group would be present at this conference, at this week, with such diverse topics as molecular visualization, eye tracking, and document analysis, and that we would have projects in digital humanities which we can still publish in this week. So I think we were really successful in keeping the lid on this expanding universe. Third problem, are our publications visible and being cited? I still consider it a major milestone for our field, especially for being acknowledged from the outside, that we managed to get the papers of our top conferences into our top journals. IEEE VIS with all 3 conferences into TVCG and EuroVis into Computer Graphics Forum. This is not only important for citations and academic careers, but also for this unifying aspect I addressed before. Fourth problem, and last I want to address here, is can we provide and grow academic careers? Although I followed some of the academic careers of people in our field in several countries, I can only do some counting from a German perspective. So when I became professor for visualization more than 20 years ago, there were only very few people in the field. Today, I would consider more than 10 full professors in Germany being primary members of this community as we meet here. This growth is, of course, related to funding, successful attracting research money, and especially from my perspective, visualization has been incredibly successful in attracting funding from the German Science Foundation for fundamental research, but also from applied research from the European Union. So in summary, I think we as a community have solved a number of structural problems with great success to make visualization what it is today. And I also think that it's equally important as solving specific scientific and research problems discussed by our co-panelists. However, the problem with structural issues is that they are usually a moving target. So in contrary to what I said before, I will address some unsolved problems. First of all, I think growth. We have seen an enormous growth at conferences, whether it's here or EuroVis at other conferences, in number of attendees, parallel tracks, associated workshops, symposia. It's amazing, but for me, it's not so clear how we find the correct balance in this growth. We want many people to actively contribute to the conference so that they can come here, and therefore we accept many submissions to various tracks and venues. On the other hand, quality-wise, there might be room for a more compact program, and it's unclear how we eventually deal with that. The second issue I want to address is internationalization. I think Pacific VIS has seen a great development, but only moderate growth. Similar things like the visualization workshop in Brazil, co-located with Grapi and others. So I really think we need to support the development of this regionalization, but it's always a problem how to jumpstart this. This is in a certain way a chicken and the egg problem, because people argue there will be more submissions if the quality increases, and on the other hand, the quality will increase if we send more submissions. So I think we have to give some credit to yeah, those rising and upcoming events in order to be more present internationally. Finally, publications. I think if you look at this journal versus proceedings, now there seems to be some friction in the process, which I heard, which used to be more smoothly. I can only appeal to the people in charge now to get their disputes resolved for the benefit of the community, because we all need sort of strong journal papers and a wide range of publication possibilities also on the conference level. And finally, unification versus variety. I would like to make a test, sort of testing conference participants, giving them only the titles of the papers and ask them to assign SciVis, InfoVis, and VAST. And I would think they miserably fail, because I've seen whether here and whether there, uncertainty here, uncertainty there, evaluation in all three. So my claim is we need to have a more unified approach here, especially from the perspective from the outside. And I'm convinced that this is a visualization problem that we could and should solve. Thanks.
Let's thank our beautiful panelists. Thank you very much. And let's get some coffee.